Thank you to the organizers. Actually, well, perhaps as David will have said on day one, I'm coming all the way from the right side of Cambridge. No, it's just a pleasure to be here, and I couldn't, I wish for a better way to start traveling again to the US after the pandemic. So, well, as of late, I've been interested in problems at the intersection of statistics and optimization, particularly around this phenomenon of implicit regularization. And so at the high level, right, implicit regularization is referring to the regularization effect that is imposed as a byproduct of the very choice of the algorithm one chooses to aim, at the very least, minimizing the unconstrained, unpenalized empirical risk function. And well, it comes under different names, right? Some literature call it algorithmic regularization because, well, it is more upfront, the fact that the algorithm has an effect. In fact, if you look into the online learning literature, the very parts of these solvers, they're called regularizers, right? It's very much explicit there, the fact that the algorithm has an effect. The term implicit comes from this line of work motivated by understanding neural networks. And in that sense, right, understanding how some properties are revealed in a way that people, well, by running the solver in a way that people wasn't necessarily aware of by the very choice of the algorithm. Anyway, so just to say there won't be neural networks here, it's just linear model and kernels, really. And it's very much try to, one of the driving force that motivates me in looking at these type of problems is very much the idea of developing and applying tools from high-dimensional probability to the understanding of these simple first-order methods. And there will be the connection with uniform learning. So uniform convergence, uniform learning, right? It refers to the fact that in some error decomposition, all of a sudden you can have an upper bound by adding a supremum. And this seems a very bad idea, but it turns out that in many settings, that's good enough to achieve minimax optimality. This is one of the main proof technique we have since the work of Vatnik and Chandelinsky, so going back 56 years ago. And that's, right, is a wonderful, right, many notional complexity you might have heard of. We see dimension, indeed, but before that, Rademacher complexity, covering numbers, and so on. Entropy metric, they all come through this line of thinking. At the end of the day, there is a supremum of a function of many random variables, and you want to understand how that behaves. And that has led to a prolific literature, right? But all in the explicit regularization framework, where one has an a priori idea of the function class over which to take the supremum. And when it comes to understanding first-order solvers, the way this uniform learning approach has been utilized is either coming out of I would say, right, just staring at some equation that you have manipulating kernels and things like that. So all of a sudden, you realize what to do with eigenvalue, eigenvectors has to do with some Rademacher complexity. Okay, there are some works that all of a sudden realize, okay, there is some complexity there in this direct computation. A more principal approach is that of, well, you care about understanding gradient descent applied to the empirical risk. In order to use for uniform learning, typically people introduce a fictitious device, which is gradient descent run on the population risk, if you had access to it, right? And trying to control the deviation. And so what motivated us, a part of this work was really trying to understand if there was a more direct connection in simple models between uniform learning and, again, the implicit regularization effect of simple models. So anyway, before getting there, I figured actually to take the opportunity to zoom out a little bit. So I will introduce the problem from scratch and going through actually some of the main error decomposition in the explicit regularization domain. And that I will use that to motivate why we should care about implicit regularization. And that I'll go through a few works that I've done all the way, right, to motivate some general theory in that respect. And a lot of what I'm about to tell you is joint work with Varun Kanade, so colleague in the CS department at Oxford, and Thomas Vaskevicius, who was a former student of ours, is now postdoc at the EPFL. And I'll comment about other works here and there, particularly a work with Dominic Richard, another former student, and Edgar, Dobry, and UPenn. So here is a problem formulation, and there are variations of this, but let me be very concrete. So we are given n data points. We model them as random variables. This is the setting of supervised learning, if you want, or regression. Think of the covariates, the feature vectors living in a certain d-dimensional space, right? And the corresponding responses. Well, we think of all of them coming ID from a certain unknown fixed distribution. The only assumption I'm going to put when it comes to this general theory on the distribution is this one. So the responses will be bounded. So we are really thinking of results in this agnostic framework as opposed to well-specified framework, though we'll mention results also there. And then, well, given this training data set, right, we proceed by choosing a loss function from a certain family of loss functions. So typical result, right, involves some property of this family, say convex, Lipschitz, and so on. And then, well, we define this notion of population risk. So that capture for a given choice of predictors, right, variable that given an X output, a predictor for the corresponding Y, right, this population risk captures in expectation with respect to a new data point coming from the same distribution, the loss that our predictor achieves there. And I should say these days, well, again, there are many implementations of this framework. Depending on the community you're part of, you might be using different letters here, right? So if you are a learner theorist, you will use H for hypothesis class. If you come from optimization, you will use W. If you do statistics, you will use theta. So here, I just, well, to be unbiased, I just picked the first letter of the alphabet. Okay, there's still a bias, I guess. This is the Latin, the Roman alphabet, right? But fine, I'm Italian. Yeah, given, yeah. Well, yeah, given some setup, right? A natural question is, how can we design an algorithm function of our training data? Training data is random, any function of them will be random, possibly with an extra source of randomness, right? Think of stochastic gradient descent. There is an external source of randomness. So anyway, how can we come up with a certain function of our random variables, training set, so that the population risk achieved by this predictor is as close as possible, right? With respect to the best predictor in a given family. And here I draw the fact that the family of predictor we might construct, the range of them might be in general different from the range with respect to which we want to compete. So there are settings that are typically called improper setting. I'll come back to that towards the end of the talk, where, for instance, to achieve certain rates for this object, 1 over n, we need to choose a larger family. Hey, this is dictionary learning, if you want, where here this can be a collection, a finite collection of bounded function. And in order to compete with the best of them, we need to go and achieve a rate 1 over n. We need to go away from the set itself. Okay. But yeah, given this setup, there are two things immediately. One is a statistical notion. What does it mean for this object to be small? The other is the computational side of things. And natural notion of optimality one might try to achieve, right, from a statistical standpoint is the minimax notion. So try to come up with an estimator that does in expectation with high probability as best as as well as the best estimator over a worst case realization of our problem. So there is a fixed distribution behind the scene and a fixed loss function. But when it comes to competing with this minimax, right, we're competing to a family of loss function, for instance, all the loss functions that are convex and Lipschitz, right? So we can have a rate that depends on the Lipschitz parameter here. And right, a supremum over all distribution here, right? Any distribution satisfies this bounded assumption on the covariates, for instance. And right, so this is from the statistics side. So we're interested in non-asymptotic result here. And from a computational perspective, well, ideally, right, you would like an algorithm that scales linearly with the data. So this is the time it takes to read from memory n point, each of them being d plus 1 dimensional. And right, if you have an algorithm that runs in linear time with respect to it, you'll be happy. Of course, you can not always hope to achieve both of these things, right? There are trade-offs, as we well know. At the same time, classical setting in learning theory, so loss function, convex, and Lipschitz, we know how to achieve both desideratum. Okay, and there is a question, what is the algorithm that does this? And is stochastic gradient descent, stochastic mirror descent in general? And how do you prove it? Typically, this is all in the explicit regularization framework, typically using uniform learning. It's not the only approach. There are others, of course, but so there are settings where we can indeed achieve both. And I'm going to comment again on a setting of interest where we can achieve both later today. But then, and I should also point out, here I mean modulo universal constant. There are settings where the constant is very important, right? Compressed sensing or, okay, Florent is no longer here. Some of the graph Florent presented to us yesterday with phase transition, those were phase transition in the universal constant. There were a graph as a function of D over N, I guess, right? And the drastic drop in the excess risk error was happening as a function of the universal constant. Here I'm only going to speak about modulo it. And then there are other notions of optimality. From a memory perspective, if you do online learning or these type of things, what the best you can opt for is to have an algorithm that doesn't need to store, right, a data set only one point at a time. Or from a distributed computational perspective, well, if you have n machine, you would like your runtime to scale as 1 over n. And here, right, just to say something about graphs, I've done work on these. There is, well, a growing line of research that looks at distributed data and doing computation with a decentralized graph, actually. And it turns out that the classical protocol to communicate information, this gossip protocol, whereby a node wakes up and chooses one of their neighbors and communicate with them, typically taking averages. If you do this type of process, the speed at which the algorithm runs is controlled by 1 over the spectral gap of the graph. Meaning that if you want to achieve a linear speed up with the number of machines, you really need to be in a complete graph or expander. But that is a story if the function that you want to minimize are arbitrary and deterministic. If you have an extra layer that comes from statistics and each agent has statistical regularization coming from the same distribution, which is very much this framework, right? They're all IAD from the same distribution. You can use some concentration phenomena and really there is a trade-off, right? The more concentration you have, the less communication you need to achieve so that you can indeed achieve a linear speed up, even on a ring topology, okay? And the way the spectral gap manifests himself is by the requirement of how many data points per agents well, we need to have in the system. Yeah, anyway, and there are many other notions of optimality and right, privacy is still fairly new, many definitions there, but hopefully you get the picture. So this is what we would like to do. And again, I know how to do this, and there is a lot of research working with explicit regularization in some example. I have to tell you what that's about. So first of all, what about the algorithm? So this is the function we want to minimize. The function is not known to us because we don't know the distribution, so we cannot take the expectation. So, right, a typical approach is to consider the empirical risk. This is a function we can compute. And well, what about minimizing the empirical risk? Well, in general, that would be a good idea if you had infinite data, because by the law of large number, this object converges to its expectation, which is the population risk. But in general, because life is finite, you need to regularize. This is a general statement. This is not always the case, right? We saw Andreas talk yesterday of some regimes where there is no need to regularize in linear regression. But right, what is the difference between explicit and implicit regularization here? So in the explicit regularization, the way we typically regularize is choosing this empirical risk and either adding a penalty term or in some setting equivalently under complexity assumption, looking at some constraint set. And right, in this side of the world, basically there is a separation between statistics and optimization. So statistics is very much about choosing this family. So, right, choosing a subset here where we want to focus on. And once statistics comes up with the prescribed choice of penalty term or constraint set, then this becomes an optimization problem. And the community in this respect has in some sense split it among people looking on the statistics side and optimization side of this problem. The implicit regularization way of attacking the problem is philosophically different. The idea here is to consider the empirical risk without doing anything to it and run a solver that is aiming to minimizing this this problem. But try really to, very much interpret the iterate of the solver as a sequence of statistical estimator. And here the goal is to connect all properties of the solver. So starting point, stopping time, learning rate, so step size, right? Everything, the very choice of the algorithm. Try to derive a direct connection between all these properties and the effect on the excess risk, on the minimization of the population risk. And right, very quickly, explicit regularization, let me tell you the typical type of error bounds that are happening in that side of the world. So, right, think of a well-specified setting where in linear regression, this is the, say, the object that generates our data, right, with linear transformation with additive, say, Gaussian noise, just to have an example in mind. So the typical error decomposition goes, well, this is the object we want to understand, right? And as an algorithm, we now choose the empirical risk minimizer over this constraint set. And so we typically add and subtract what happens to the population risk achieved at this minimizer. So this is captured by this estimation and approximation error term. Approximation now is just a deterministic error term. So throughout the talk, if you see something capitalized, it's random. So this is just the error that we commit by having a bold there. And whereas all the randomness is encoded in our algorithm in this term. So if we now take the estimation error, the typical error decomposition, the variation of this goes by now adding the empirical risk, because ultimately you want to use the fact that this is any minimizer of the empirical risk, so the empirical risk should appear, right? So you add and subtract the same terms, and you use the fact that in this is a minimizer, so this object is at most 0 for any value, in particular for this value that you have there. And if you do that, so you remove this term, having an upper bound, you're left with, two terms that are symmetric here that captures the population and empirical risk. And then there is this optimization error. So putting everything together with approximation here, you have what I call statistics and what I call here computation, which is really the optimization error. And here I'm already doing what, right, is this uniform learning approach. So to remove the randomness from the algorithm and only deal with a term that has the randomness in the empirical risk, we take the supremum, the worst case scenario of the ball we are restricted ourselves. And this is, again, there are variations, but this is one of the main error decomposition that people have been using in statistical learning. And well, what are problems of this error decomposition? So let me quickly, actually, let me say, right, separation, right? You can think of this as an optimization problem. A lot of literature just looking at designing solver for this optimization problem. It is an optimization problem with a specific structure because this is a sum of, this is an average of function that you want to minimize. So there are a lot of, fast solver that use some, oh my God, what's the name? Variance reduction technique that are aiming at minimizing function with these structures. On the other end, you have these objects, which you can very much try to understand using tools from high-dimensional probabilities. And one of the main tools is this notion of complexity. So these are IID Rademacher random variables, so symmetric Bernoulli, and a very simple symmetrization argument immediately leads controlling this quantity by this notion of complexity. And right, further upper bound from it. So if you have a VC dimension log over a number, they will come as upper bound with this quantity. Now, one problem with doing this type of process is that the Rademacher complexity can be shown to be lower bounded by order 1 over square root of n. So people have been, right, there is a long line of literature starting, I guess, from Bartlett, Bousquet, and Mendelsohn that tries to localize this type of error decomposition and framework, leading to other notion of localized complexity. And this is a recent notion of localized complexity from this paper by Liang, Sasha Rackling, and Schildonen. And this is what is going to be relevant for us. In some sense, there is an extra term that captures that can be used to localize the function class over which you want to understand, the complexity. And one way in which this new notion of complexity has been used is actually to exploit the fact that within explicit regularization, once you constrain on the ball, your empirical risk minimizer satisfies something more than what I told you before. Before I told you, and we were using this bound, but actually you can prove this is a consequence of first order optimality, that this object is at most, well, upper bounded by something non-positive. And this is going to be relevant for us later on. Yeah, let me tell you some problem with these are the compositions now. So first of all, if you look, these all for the empirical risk minimizer, right? That's one thing. We use that property, but even in that case, there could be setting where two different global empirical risk minimizer achieve very different rate on the left-hand side, but this is not reflected on the right-hand side. Any empirical risk minimizer here will right, or approximation to it will cancel or make this term small, but there could be very, right, what I said before, there could be a large deviation when it comes to the choice of the optimizer on the population risk. This is one problem. From a computational perspective, well, these are composition assumed. So if you want to achieve a minimax bound, if someone gives you a lower bound or rate you want to achieve, you want to be able to upper bound all of these terms with respect to the same rate. And this assumes that you can come up with an algorithm that can make this optimization error as small as possible, but this is with respect to the global minimizer of the problem. So it's not clear that we can have tractable algorithms to do that. And then from an approximation perspective, well, all of these, again, you're comparing with a reference class B, but to run this procedure, you need to choose, right, model class A. And there is a question on how to choose in it. And again, this is done in a lot of contexts in statistics and machine learning, right? This boils down to what is the question, what is the choice of hyperparameters, of regularization parameters that leads to optimal rates. But all of these, right, this is the way I'm thinking about it, and I'm using it here. All of these prompts for understanding really what happens if you look at a solver, apply to down-regularized empirical risk, and try to understand the statistical properties of it. And so these are a few of the papers I have on topic related to implicit regularization. I want to comment on a few of them. So first of all, right, I think this picture is helpful to start the stage. This is looking at a linear regression framework with square loss. And let me consider two estimators, or well, yeah. One is a very, right, so let me consider rigid regression here at this level, parameterized by lambda, the parameter controlling the strength of the regularization on the one end, as opposed to gradient flow. So let me look at continuous time methods here to begin with, aiming at minimizing the regularized empirical risk index by time. And again, there are different ways to express this. I like this picture in particular from this paper by Ali et al., where they show here what we are seeing, right? This is our population risk plotted for the gradient flow as a function of time. So time going to 0 to, right, towards infinity. And this is the regularization path traced by gradient flow there. And then you have in black the regularization path traced by rigid regression, plotted as a function of 1 over lambda. So the setting of overfitting in general will be the case where t goes towards infinity, and the case where lambda goes towards 0. And this is a case where we have that, right, our U-shaped curve. There might be other type of curves, right? If we are in a regime where zero regularization is a good idea, you will have another shape. But no matter, right, the shape is not the point of this plot. The point of this plot is comparing these two curves. And this is a strong comparison because you can pick any point in this axis. And what they showed is that actually there is a universal multiplicative factor, something like 1/6, whereby the two curves are multiplicatively away by that factor. So not just comparing what happened at the minimizer of both curves, but really along the regularization path. And well, you might ask, okay, why there is this connection? And there are, again, different ways of seeing this. You can unravel gradient descent in discrete time, realize that you're dealing with a truncated Newman series. So you have an approximate inverse that is very much related to the inverse you have in the solution of ridge regression. Just to have, I guess, an intuition that will be helpful later on, you can see that you can write now in discrete time, this is the step size, gradient descent, one iteration of it, as you can think of it as minimizing a quadratic, right? You have a linear expansion plus this quadratic or proximal term. And so you see that the connection between this L2 regularization of gradient descent, right, is manifested here by the fact that you have the square of the Euclidean norm. And just to say, and actually, okay, this story is all well and nice, and it has led to a lot of results, particularly in the kernel literature. One thing that I briefly want to touch base upon is that the moment you start discretizing, there could be, well, what was a surprising phenomenon to me, in the sense that you could be in a regime. So what I mean by discretizing, let's now take a grid. Let's compare the two methods by taking grids. So in the case of ridge regression, well, I can take a grid of parameters because, right, on our computer, we have finite whatever. So we can take a grid and we can take uniform grids or, you know, logarithmic grids, which I think is what is happening if you code this thing in Python. And look at what happened once you have a grid there. You can look at what happened for the error achieved by ridge regression. And you can compare this grid, this finite family of estimators, each indexed by a choice of regularization parameter in the grid, with what happens if you run gradient descent for a finite amount of steps. Because, right, if you run gradient descent for a finite amount of steps, you have a finite collection of estimators. That doesn't really correspond to putting a grid there and looking at what happened at the red curve, because, of course, in order to go from one point to the next, you have a discretization effect, right? In the case of ridge regression, per any choice of lambda, you're solving a new optimization problem if you want to get to the corresponding error. In the case of gradient descent, this is done sequentially. And if you do that, and you compare the two grids, you might end up with a situation like the following. And this is just a plot for this paper that we have with Dominic and Edgar, where we show that in some regime, right, ridge regression, which is an optimal estimator, in this case, is base optimal, if properly tuned. Okay, you can see this. If properly tuned, ridge regression is always giving you the optimal error. The moment you have this grid going on, there could be in a situation where a ridge regression is outperformed by gradient descent. So here what we're plotting is, so ridge risk means the best, so the lowest error among this family of estimator indexed by the grid for ridge regression, minus the best error achieved by the corresponding grid or along the path, right, for gradient descent. And so this plot is always positive. So you're always normalized by the optimal risk. And this plot is always positive. So gradient descent is always outperforming a ridge in this grid. And in fact, it will be outperforming ridge by an unbounded amount. Yeah, in this paper, we characterize what happened in different regimes. We have some understanding of what is going on. This is a case, for instance, when the empirical covariance matrix has a spectrum that decays slowly with a power rate with exponent less than 1. If you are in a case where the spectral properties of the empirical covariance matrix decays faster than that, the opposite will happen. You can drive, right? But at that point, and here I just give this as a teaser, I guess, because I want to focus on this connection with uniform learning. You can be in a regime where one method on the grid, the best, right, choice in this family is leading you to better result for either ridge or gradient descent. Actually, in very simple setting, in the case where the empirical covariance is isotropic, we can explicitly look at what happens to, there is a new, we connect this type of idea with the notion of minimax mean optimality, where we have two mean now. The first mean is over the class of estimator. The inner mean is over the best estimator in the class. And in simple cases, we can really compute this min max mean algorithm And it turns out to be equivalent to gradient descent with time-varying learning rate. Anyway, but just to say that this general connection between ridge and gradient descent has been explored in a variety of settings and has led to a prolific literature that really aims to achieve minimax optimality by speeding up computations. And all sorts of techniques have been added here to the basic gradient descent mechanism to speed up computation or to reduce the amount of memory that is required, always trying to maintain minimax statistical optimality with high probability. And so, right, when we started looking at this type of question, one motivation came from the Lasso estimator. So after all, right, a lot of high-dimensional statistics has been driven by this problem. And so what about an implicit regularization analog for this problem? And we look at the literature and back then, this is a couple of years ago, this type of connection has been made in different settings, but typically most of this connection, we're looking at things at convergence with zero or small noise. And okay, we want to understand what happens if there is a classical statistical settings with noise in it, and aiming, right, at achieving simultaneously statistical and computational optimality as I define them. And the starting point was this realization. It was first made as a conjecture in 2017 and then proved in some setting that if you look at gradient descent with a certain type of parameterization, this Rademacher parameterization, and you initialize the algorithm with a small initialization, actually the algorithm will lead to sparse solution. Along the path will maintain sparse solution. So you start the algorithm from all the coordinates being very close to zero, so we are very close to being sparse. And as you run it with this parameterization, the sparseness is preserved up to a certain point. And so what we really wanted to do, yeah, please. In the first, yeah, there is this line of literature connecting boosting with the limits. The limiting behavior, what happened t going to infinity in the zero noise to L1 regularization, in fact. So various authors, so there is a general theory that does this by Gunasekar and Srebro, where they look in general mirror descent, and they characterize what happens to the limit point as a function of this the potential function that defines mirror descent anyway, and they have this connection. So one connection in particular is with data boost or coordinate descent. So anyway, yeah, those type of results typically looking again zero noise at convergence. They typically follow from KKT optimality conditions. And all right, so we started looking at the sparse recovery problem using this type of idea of this Rademacher parameterization. And we really want to understand, right, how far we could draw this theory there. I quickly want to glance a few ideas and results. So this is the setting. Okay, I go back to my W notation here, but I guess we're all familiar, right, with sparse recovery. The condition under which we can prove something for the algorithm we are looking at is using this RIP condition. A very strong type of RIP where the delta parameters here that control the approximation actually depends on the sparsity level in this fashion. So this is in fact not optimal, right? But we couldn't drive the theory beyond this point. But I guess, right, let me not spend too much time on this. I really want to flesh out a few results. So under this RIP condition and what we can do, we can look at, this is the unregularized empirical risk with this parameterization. So this is the Rademacher parameterization that allows to have negative values as well. So this symbol means just taking coordinate-wise product between the coordinate of the two vectors. And this is what the algorithm looks like if you run gradient descent just on these two parameters, U and V. So at each time step, you update U and V. And well, right, at the high level, how can there be an intuition that whatever we're doing this here is connected with L1 regularization? Is the fact that if you take what I told you before, the gradient descent is linked with L2 regularization. the moment you look at, well, this parameterization, right, you run gradient descent on the U variables. Let's assume the case that there are no negative values here, just for the sake of simplicity. The moment that you look at the, right, the square of the Euclidean norm for this parameter, you end up with the L1 norm for the parameter A. So this is just intuitive, but just to say that there is, right, hope to be able to do something there. Okay, I might spend a few more words later on. Very quickly to glance out the result, but under some condition on the initialization size. So we initialize from a vector of full ones multiplied by alpha. Alpha needs not to be larger, too large. And same thing for the learning rate. Doesn't need to be too large, where this alpha max is the maximum size of the coordinates. And this is something that can be estimated, right? Fairly easy. We end up with an early stopping result where we say, okay, there exists a time. We provide an upper bound for the time that depends on these parameters. So in particular, there is the dependence on the maximum value and the minimum value of the signal, the typical noise term that you have in this type of problem, and epsilon, right? Any epsilon that you choose over there, along with the size of the initialization, so that we can control what happens, the error that occurs outside of the support, as controlled by the size of the initialization, right? So here you see there is immediately a trade-off, because you want the size of the initialization to be small to control the off-support error, but that will make your stopping time, at least this upper bound, bigger. And inside the support, we have this bound. Okay, here I present two versions of it, but anyway, we can control the error, what happens there. And in fact, I mean, there are corollary and consequences of this type of result. If you are in a situation where the minimum value of the signal is larger than the value of the noise, you are in a situation where you can prove that this algorithm not just achieves the minimax rate of the lasso, but it can beat the rate of the lasso because it can have, it can remove dimension dependence in the log term, replacing it with a dimension of the sparsity level. This is just to emphasize, all of this can be done. And, you know, we have plots that corroborate the, right, for instance, the trade-off I told you about, that the smaller alpha, the smaller the error, but the longer the stopping time. And this is just to emphasize how, I think, well, what is the role played by the size of the initialization, or what the regularization path looks like. Essentially, this algorithm, as a function of time, learns one coordinate at a time. And the whole goal here is to have an initialization side that is small enough so that you can fit all the signal coordinate before you start fitting the noise. And at least we can drive the story in depth completely if we have RIP properties there. But anyway, just to say very quickly, if you instantiate the theorem I told you before with some specific choice of epsilon, you end up with minimax optimal rates. There is a question of what is the upper bound for the stopping time, because I told you we would like to have something that is computationally optimal as well. This doesn't get you there because it says, okay, you need square root n iteration. Each iteration, this is full gradient descent, takes, right, order n. So we are not there. But a modification of this algorithm will increase the learning rate of some coordinates, not all of them, can get to a final algorithm that runs in linear time. So this is all nice. And I think as a proof technique, by the way, this approach of looking at the Hadamard parameterization has been considered by many authors. And long story short, I mean, the main essence of the proof can be reduced by understanding what happens to the signal coordinate of the algorithm, the coordinates that are on the support of the true signal and the other coordinates. And it boils down to, in this case, very much understanding, so right, this very much lower level argument, understanding the behavior of one-dimensional sequences that have this structure. So if you take the algorithm I told you before, and you replace this type of construction here by the identity matrix, everything decouples, you're left with one-dimensional sequences. And it turns out, right, all these sequences, they increase exponentially fast, but with different rates. And so the whole goal is, as a size of the initialization, that's what you want to control, to tune, you want to fit the signal before you start fitting the noise. And again, under RIP, you can do this. Anyway, this is just to glance out a few ideas. Yeah, here you see how it is qualitatively different from what happens with the Lasso. And now each coordinate on the signal under RIP are fitted one after the other before you start fitting the noise. So here is where you want to stop, right? Thinking of early stopping. And this is what happens with the Lasso. So anyway, I would like to skip this idea of how to achieve computational optimality, though it's pretty cool in a way. We have increasing learning rates. Increasing, right? You typically think of a step size of a learning rate as either being constant as iteration time or being decreasing with iteration time. This is one setting where you want to increase the learning rate. And there are many results in reinforcement learning. This has been done to get linear rates recently. But you know, this is all news, and we can really nail down what happens there in this equivalent to the Lasso. It is a bit, it falls short in providing us with a general theory, right? It's very much going down level, doing this perhaps tedious manipulation with sequences, and there is no probability. And yeah, and that is, in a way, what motivated us to try to zoom out and establish a general theory here. So a connection with what I just told you. So first of all, what does mean general theory? Is clear when we apply gradient descent to this parameterization formulation, the algorithm is something different, right? We are playing, we would like to exploit the geometry behind this sparse problem. We can achieve that using the parameterization, but maybe there is a more elegant and general way of doing that. And this general way goes under the name of mirror descent. And in general, we know how to play with the geometry when constructing this first order method. So if this is gradient descent, for instance, right, there are situations where even minimizing a quadratic gradient descent with zigzag. But if you apply Newton's method, you can converge in one step. And Newton's method in this proximal representation is very much adding your Hessian matrix there as a way of rescaling the problem. So, right, Newton method is one implementation of a deviation of the standard gradient descent algorithm, the way I'm presenting it here, that allows to exploit different geometries. One problem with this method, well, you have to invert the matrix, but even just storing the matrix takes d square time. So if you want to achieve statistical computational optimality, n times d, just reading from an Hessian matrix is not getting you there. So you can think, okay, we can approximate this object. But really, what I want to use these slides for is to motivate what comes next, which is this general definition of mirror descent. So, right, in a way, we would like to change the geometry, but in a way that we are not increasing computation and perhaps doing something right beyond just this simple scaling. So this can be achieved by this family of algorithms, where you see the proximal term is now given by this Bregman divergence as a function of a given potential function of mirror map that you choose. So different function of mirror maps will lead to very different looking algorithms. Right, this is no longer a distance, this Bregman divergence is not symmetric, but it shares a lot of the property of the square Euclidean distance, so we can do a lot of theory with it. And this is just a table representing a lot of these Bregman divergences. And going back to the connection with the Lasso, if you take this particular Bregman divergence, and you look at what mirror descent with this Bregman divergence looks like, you end up with this so-called exponentiated formulation of gradient descent. And if you take the first order Taylor approximation of the exponential, you end up very much with this algorithm, modulo constant. Okay, so the algorithm we were exploring before can be thought of as a first order Taylor truncation of mirror descent with this particular mirror map, where alpha is the size of the initialization. And this just to connect, right? So what we've done before, we have a way of understanding that algorithm in more general terms. And now, as a matter of fact, there is a recent paper by, I think, Hasan's group at Princeton that is showing one-to-one correspondence, although it's constructive only in one way, where a certain type of Hadamard parameterization is linked with a certain type of potential function, at least in continuous time. Anyway, let me get to the main result that I want to discuss. So this result is about this general family of algorithm called mirror descent. So in continuous time, this is what it looks like. This is your potential function. These are, okay, the assumption I told you before. This result was for linear model of kernels with the square loss of strongly convex loss under only the assumption of the boundedness in the y's. And the picture is the following. So you start the algorithm from a certain initialization point. B star here represents in a well-specified setting, right, the minimizer of the population risk. This is what you like to compute. You run your algorithm on the empirical risk without constraint penalty term. The algorithm will follow a certain path. And what we were able to show is that there exists a stop in time. This is a random variable, right? Depends on the training data in particular. We give an upper bound for it, such that at the stop in time, the same condition I showed you before, if you remember, that what was achieved by the empirical risk minimizer in explicit regularization, the same condition holds up to a certain threshold epsilon that we can choose here. The smaller the epsilon, the bigger the upper bound for the stop in time. Anyway, this condition holds, and before and any time before that stop in time is such that the algorithm stays within this region, this ball. And now this ball is non-convex in general, is defined here in terms of the random divergence. It is centered at B star. Yeah, this is the type of high probability bounds that immediately comes as a result. We have that the population risk achieved by our early stop mirror descent algorithm with respect to, right, the best possible minimizer is upper bounded with high probability with something that depends on the 1/n with your confidence level here, and with a complexity that is given by the offset complexity, a notion of it similar to the one I defined before. And so just to emphasize, I think the way I'm thinking about this result is fairly general, okay? And it gives a tool to understand the property of these early stop algorithms with respect to this notion of complexity with respect to this ball. So this is not a ball that you choose a priori, right? It's very different from explicit regularization where you choose the ball a priori and then you run your theory. This is very much the ball that you choose is centered around B star. And of course, it depends on the initialization of the algorithm, but then it's very much prescribed by the choice of the potential function, the shape of it. And so I think once you have this result, okay, we have example where we instantiate this result, but I really think of this as a tool, as a general tool. And right, you can play the game of trying to develop new first order method, for instance, that achieve this condition, but with less iteration. Right? Using, if you remember the list of algorithmic primitives that I showed you before that has been used in the kernel literature in connection to rigid regression, you can try to do something using, right, some of those primitives to speed up computation so that this condition is still satisfied. And okay, yeah. Yeah, in the case of ERM, but you need to prescribe the ball over which you want to choose empirical risk minimizer. I think that's one of the main takeaway. So indeed, if you have this Rademacher complexity with respect to this set, yeah, if you have this set, well, this is the Rademacher complexity of it. But the point is that this set is prescribed by the choice of the potential function, so the very choice of the algorithm you run, and it is centered around the unknown object you want to recover. So I think this tool actually can be used as a way to separate implicit and explicit regularization because of the way these balls are constructed. If you think of the Lasso of rigid regression, there you run your ERM, but your ball will be centered around 0, not centered around the true population risk minimizer. Anyway, very quickly, my time is almost up. I want to tell you the proof of these results. And I think is I personally love this proof. So this is typically the way people use convexity when analyzing first-order method in optimization. You use the fact that if you're dealing with a convex loss by convexity, right, this is the definition of convexity, which, right, in the case of a continuous solver can be also expressed in terms of this derivative of the Bregman divergence. The way the proof of the result I just showed you comes about is by filling this convex inequality and actually realizing that the same identity here is satisfied, right? If you add, right, you can make this inequality an equality by adding this term. And this in-prediction error term is precisely the term that defines what I call the offset condition. So the condition I had in red here in this theorem. And once you fill an inequality with an equality, I mean, you think you have restored a bit of order in the universe when the additional term has a statistical meaning, right? And so the rest of the result is just a simple integration. It really is this slide is integrating this quantity using fundamental theorem of calculus and the fact that Bregman divergence is non-negative. Yeah, this is to prove that the offset condition is satisfied up to epsilon. And then, right, to show that you stay in that ball before it is very simple. And yeah, these are just some simulation involving your empirical risk, success risk, and what happens to this Bregman divergence. And right, what we are saying is that ideally, if you have access to it, this Bregman divergence depends on the population minimizer. If you had access to it, right, our theorem will prescribe to stop at the last point where this object keeps decreasing. Yeah, I don't want to steal more time. There is a question of, okay, once you have this condition, this offset condition, how can you get high probability bounds? And this is what really drove us to really develop what can be considered a dual theory that leads to this type of error rate, avoiding the Bernstein condition and using this offset condition. So for those of you familiar, the Bernstein condition is one of the main sufficient conditions that people use to instantiate the framework of localized Rademacher complexities. And what we are doing, we have actually shown, I think I'll skip everything else, but I have a slide that makes that point. Classical theory of localization for the empirical risk minimizer. So assuming this Bernstein condition, you have high probability bounds with the fast rate with respect to this notion of complexity. The theory we have developed, we swapped this Bernstein condition with this offset condition. We are showing that any estimators that satisfies this offset condition, and I told you at least about two, right? Empirical risk minimizer satisfies it. In explicit regularization, early stop gradient descent satisfies it. But any algorithm satisfies that condition will lead to high probability error bounds with the fast rate 1/n in terms of this notion of complexity. Here, yeah, I don't have the time to tell you detail, but really this offset can be thought of as a dual, as an empirical version of the Bernstein condition. Okay, to wrap up quickly, I think, right, we have some general theory of what happens to mirror descent, early stopping it. If you need to early stop it, it's not necessarily the case that you always need it to achieve minimax rate, right? Under this notion of complexity, I've looked at instantiating this type of ideas for sparse linear recovery and sparse phase retrieval, though there is still a bit of a gap, right? Because really nailing the problem in these two settings requires to go to lower level arguments. So there is still a gap on how to use this more high level theorem to a familiar problem of interest when you really want to achieve the best possible bounds. But this paves the way, I guess, for, again, applying these other algorithmic primitives in this general setting. And then there is a localization theory for the fast rate, which I mostly skip about, that really shows that, right, this offset condition can be thought of as a design principle. Any algorithm satisfies it will give you this type of high probability bounds off the shelf. And yeah, the connection of how that can be used to improper and non-convex method that I also skipped, but it's very much what a lot of this research is geared towards, right? Generalizing, coming up with new tools that can be applied to in this case, non-convex model as well. let me stop you here. Thank you.